Okay, so today we're going to move on to something to basically heaps and heap sort.
Heap sort.
Heaps and heap sort. Yeah, well, once you learn about heaps, you'll hopefully realize how you can use it to sort things quickly. Heaps are really just an implementation of binary trees using an array. That's what it comes down to. But it doesn't do it the same way as a binary search tree. It's a different type of binary tree. So make sure you get the two straight, that while both heaps and binary search trees are binary trees, they work differently. They're not the same. But we're going to go and talk about why heaps are so important, which really comes down to the fact that since you're using an array, you actually save a significant amount of memory. If you have a set amount of memory, you know how much you need to hold. You don't have to store extra pointers running around. But it does make some calculations a little more tricky as to what's going on. So let's go ahead and get started. Why study heap sort? Oh, okay, great. Well, this is actually, it is well-known traditional sorting. We're going to end up using heaps to sort things. It's also always in log n, so that means it's going to match the performance of merge sort and quick sort, or be comparable in performance. Quick sort, of course, usually in log n, but can go down to n squared. While quick sort ends up being generally faster, heap sort is better for time-critical applications, just similar to merge sort, because it's always in log n. So what's a heap? All right. So what do you know about a heap right now? The memory where you store, where you allocate. The heap data structure has nothing to do with that.
All right.
Okay.
Great name.
So, the stack at least made sense, like we got it, but heap, these are completely different things, all right? So, sorry guys, that's what they did. Look, history, convention, I don't know why they did. Called it anything. Yeah, they could have called it something else, but they called it a heap. So memory is a large area from which programs can allocate blocks as needed and deallocate them as needed. The data structure is a balanced left justified binary tree in which no node has greater value than the value in its parent. They have nothing, again, they have basically nothing to do with each other. That's the point. We'll talk about the data structure in a moment. Yeah, I guess their commonality is they both deal with memory. Like data structure has to be in memory. That's about it. That's all we got. Yeah, heaps and heap sort use the second definition. All right, so first let's talk about a binary tree, or a balanced binary tree. So remember, the depth of a node is its distance from the root. The depth of the tree is the depth of the largest or the deepest node. A binary tree of depth n is balanced if all the nodes at depth 0 through n-2 have 2 children. All right, that's a confusing definition, but if you look at it pictorially, it makes perfect sense. I'm just going to draw circles. We don't care about numbers right now. All right, that's balanced. That's not balanced because it needs to fill this in. Basically, if you're looking at it pictorially, each horizontal row is completely filled except the last one. So if we were to move that guy up here, now it's balanced.
So without that, it's not balanced?
This is still balanced because, remember, every row except the last has to be full.
Okay.
So this last one's not full, but that's okay. It's still balanced. The problem is if we added one, or even...
So if you add one, the row before that has to be full.
Yeah. Now remember the definition though, saying it mathematically, a binary tree of depth n is balanced if all nodes at depth n through 0 through n-2 have 2 children, aka he has 2 children. Well, then you wouldn't check this one because it's n-2. If we were to fill this out a little more, I'm sorry, let me go back to the definition. The reason why this isn't balanced is because then you have to check each one of these 2 nodes. While this guy has 2 children, he does not. But if we were to fill him out, that's fine. And then you put another one right here. Is that balanced? Yeah. Yes. He has 2 children, and both of these guys have 2 children as well. I'll go ahead and draw this completely out. This makes some sense. And I'm going to stop drawing it soon. because there's going to be way too many circles. All right, is that balanced? Yes, that's still balanced, only the last row. Right. Remember, you're checking n minus 2, so that'd be this level and this level. You don't have to check these two levels. You don't check the last two levels to see if they have two children. Really pictorially, just make sure only the last row is the only one without any only thing missing. So if I put one here, is it balanced?
No.
Now it's not balanced, right? Is that balanced?
Yes.
All right, last check. Is that balanced?
Yes.
Yes, that's still balanced. Remember, only the last row isn't full. You're checking to make sure he has 2, these guys have 2, and these guys have 2. You don't care about these 2. So is this balanced? Yes. All right.
You say you don't care about those two, so.
Yeah, you don't care about these 2 levels, so to speak, or at this depth.
So if there was one missing there, that would still be balanced?
Now,
Second on that?
there's two definitions I've given you, and I might have confused you. If you look at it pictorially, it's easy to see. You just make sure that each level is full except the last. The definition up there is you check everything but the bottom 2 levels and make sure they have 2 children, which is the same thing as making sure everything, only the last row is not full. And if the last row is full, that's actually okay as well. All right. Is that balanced? Yes, that's still balanced. Yeah, because you're only checking these 3, because I haven't added, if I add any nodes to these guys, then it would be unbalanced, because you have to be checking this row. Everyone see the point of balanced? Okay, great. Here, some more pictures on board. That one's balanced. That one's still balanced. He is not balanced. Where does a node need to go? Yeah. Right over here. Perfect. All right, left justified. Basically, all the nodes are shifted to the left. All leaves are at the same depth, or the leaves at depth n+1 are to the left of all the nodes at depth n. So, left justified. Notice that on the final row, all the nodes are starting from the left and then are filled in until you have no more nodes. All right. Over here, not left justified because you need a node over here. You probably need to move that guy over there and then move that one over there. So, is that left justified? No, this one's not left justified. Is it left justified now? Nope. Nope. How about now? Nope. How about now? Yes. It's now left justified. Okay. All right, so a heap has to be both balanced and left justified. That's what we're getting at. Plan of attack. All right. First, we will learn how to turn a binary tree into a heap, which actually is not too bad. Next, we'll learn how to turn a binary tree back into a heap after it's been changed in a certain way. All right, great. Finally, we'll see how we can use these ideas to sort an array. Yeah, okay, cool. The heap property. So a heap has to be balanced, left justified, and everything has to satisfy the heap property. So a node has the heap property if the value in the node is as large or larger than the values of its children. Is that the same as a binary search tree? Not necessarily the same. That's right. So if a value in the node is as large or larger than the nodes in its children. So it's not that everything greater is to the left or to the right and everything less is to the left. It just has to be greater. So blue node has the heap property because 12 is larger than all of its children. Blue has, as large or larger. So that's still the heap property because we allow duplicates, and that's still fine. This does not have the heap property. All leaf nodes automatically have the leaf property as well. You want every node has to have this property in order for it to be a heap. Let's see if it gives us better examples. Yes?
So I was going to say that means the parent is going to be the previous number then?
Exactly. That's actually the key thing to the heap, is that it's balanced, left justified, and the top node is always the largest. Okay, hold on. Let's do a couple more examples on the board so this is clear. Let me get rid of all these oh my goodness. All right. All right, give me some numbers. 56.
17.
All right. 10.
39.
17.
-5.
-5. Okay, hold on a second.
Now we gotta go lower because I'm not
-5. -5. All right, what else did you have?
-17.
-17. Yeah, we can put that here.
8.
10.
You want another 10?
8.
Hang on a second. Yeah, so we can put a 10 right here. And then what's another one?
58. 3.
58. Let's go with 3. I like that. Okay. Is that a heap?
Yes, thank you.
Yeah.
Yeah, so it's balanced, it's left justified. Every node is larger than all of its children. Notice that this is definitely not a binary search tree. All right. So if you were right here and you wanted to know what the second largest number was, what would you check?
You have the 2.
Yeah, 2 children of the node. Yeah, keep that in mind. All right. And okay, so first off, okay, sifting up. This is really how do we add to the heap? Give a node that does not have the heap property, you can give it a heap property by exchanging its value with the value of the larger child. All right, this I think makes a lot of sense when we do it pictorially.
And just keep moving.
All right, give me a number.
37.
37, that sounds great. So we can try and put 37 right here. All right, when you add, you always, remember, since it's balanced and left justified, you're always gonna add over here, you know, bottom level, furthest to the left, right now, right here. 37. Is that in the correct location? No. Here's what you do. You compare the 37 with what's above. If it's larger, you exchange them. So now you have -5 and 37. All right, let's do it again. It's 37. Do we need to exchange 37 and 10?
Yes.
All right. Do we need to exchange 37 and 56?
No.
Oh. Is it a heap? Now it's a heap. So what was the big O of that? Oh.
Oh, n minus 1.
Log of n. Why is it log of n? Yeah, so sift up. Am I on the board? I'm close. Doom. O of log of n. Because every time you sift up, you're dividing your space in half. Is the easiest way I can explain it right now. Yes?
So if it has to be smaller going all the way down, how would you sort this to be like what you want it to actually be if it can't be like small on this side, large
So
on
we
this side?
were talking about adding. Once I tell you how remove works, sorting should make perfect sense.
Okay.
Okay? All right, let's do another example just to make sure people get it. Because I think 3 examples usually is what drives it home. Give me another number. 45?
I didn't say that, but yeah.
45? Right. My hearing is not the best, guys, so that's why I'm so loud sometimes. So, what do we do?
Check with the
Check the parent stuff.
Check the parent. Do we need to swap?
Yes.
Yep. All right. Parent, do we need to swap?
Yes.
Yep. Check the parent. Do we need to swap?
No.
Nope. All right, great. Let's do one more example. Another number. Don't care what it is.
86.
86. All right.
Something bigger.
Actually, hold on. Let's do one other example real quick. Let's do -3. What do we do?
Check all parents.
Do we need to swap?
No.
Yes. Because -3 is larger than -17. And those tricky negatives. We swap the -3 and the 45, or we compare them. Do we need to swap? No. Okay. I just wanted you to note that it can stop before it gets to the top and your algorithm's done. Just O of log n is the worst case scenario. And on average, it's pretty much log of n divided by 2, which is just log of n. All right, now let's go ahead. What'd you have, 80? 86? 86. All right, compare it. What do we do?
Swap it with negative.
Yep, swap it with the -3. Okay.
Change his parent.
Mm-hmm.
It's bigger.
It's bigger, so we swap it again. All right. All right. Now what do we do?
Check his parent.
And
Bigger.
do swap? Yep. Nice and squeaky. All right, and since we're at the root, we're done. All right, everyone got sift up right?
But do you have to check that, like, if I like?
Yeah, at the end you're like, oh, we're at the root? Okay, we're done. You'll see how that's not that bad once we get to it.
So I take it we keep track.
I'm sorry?
I take it we keep track of the parent of each of these?
Yes.
Okay.
Yeah, just right now I'm explaining it pictorially because once we go to the data structure, a lot more of this will make a lot of sense. It's just that this is kind of different. This is different than what you're used to, so I'm trying to drive this home right now. All right, so sifting up, blue node does not have the heap property, so you have to shift up the 14, and then we're done. Okay, great. It's called sifting up or shifting up. I'm using sifting. Okay, good. We'll say sifting. Note that the child may have lost the heap property in this situation. All right. A tree consisting of a single node is automatically a heap. Everyone good with that? Balanced, left justified, and of course it has its heap property. We construct a heap by adding nodes one at a time. Add the node just to the right of the rightmost node in the deepest level. That is what I was doing when we were doing sifting up. The deepest level is full, start a new level. Examples, so we have this, add a node here, or add a node here. All right, everyone good with that, left justified? Good. Each time we add a node, we may destroy the heap property of its parent node. To fix this, we sift up. But each time we sift up, the value of the topmost node the sift may increase, and this may destroy the heap property of its parent. What's actually very important to understand when you're looking at this is that every time you sift a node from the bottom up, the parent is always increasing in value. It's never decreasing, which is why everything to the other side is still okay, because you've only increased its value, you haven't decreased it. So that's why we only need to keep going up. We repeat sifting up, moving to the tree until either we reach nodes that don't need to be swapped because the parent is still larger than both children, or we reach the root. All right, they go through some examples here. So they added 10, they swapped it. They add the 5, we're good. We're gonna add the 12, what happens here? Swap with the 8, and then we got to swap with the 10. All right, good. Oops. Again, other children are not affected because, yeah, okay. Swap the 14. Obviously, that 8 is still smaller, and then you swap. Yeah, this 8 is not affected because its parent always gets larger, not smaller. And then swap the 14 and the 12, and now we're here. 5 is not affected because its parent gets larger. That's the trick with sifting up, is that it only gets larger. But here's an example after it's been a tree, binary tree has been heapified. That is actually a technical term. Yeah, you can, in the STL it has heapify. Don't use that for your lab.
Heapify.
Yeah, it's called heapify, or make heap. Ah, that was the big one. Notice that heapified does not mean sorted. Obviously, this binary tree is not a binary search tree. Heapifying does not change the shape of the binary tree. This binary tree is balanced left justified because it started out that way. All right, removing the root. All right, so here we go. Let's do this pictorially. So when you remove from a heap, you always want to remove from the top. Don't try and remove somewhere else, sadness will occur. You always remove from the top. And that actually is kind of nice because what did we know about the top? Someone said it earlier. It's the largest. All right. So we're going to remove the top, the 86. We'll put it right over here. We'll pretend like we're making another array. All right, we removed the 86. What should we replace it with? I'm sorry, what? Okay, you're thinking ahead. We want to make sure that it stays balanced and left justified. Just to allow that to happen, which node would we put up there? Just to keep it balanced and left justified. Which is the -3. So if we move the -3 up, right here, it is still balanced and left justified, right? And we've only done an O of 1 operation. We haven't had to search or anything. Right now, by moving that -3 up there, it's balanced and left justified. We haven't broken that property. That's great. The only thing we have problems with is we have to maintain the heapify, or the heap property, which, is that the case? No. So here's the trick. When we added, we sifted up. What do you think we're going to do now? Sift down. Okay. All right. So how do we sift down? We take the -3 and we compare against the two children. Which of the two should we swap it with? 56. Why? Because it's bigger. It's the biggest of the three.
So, with the remove, you can't remove a specific one, you can only remove the top.
Don't do that. That's not the purpose of the heap. Is really the best way I can answer that for you. If you can do it, I don't know why you would, but that's not what heaps were meant to do. So that is a restriction of heaps. You could try and do it, you will be very, very sad.
It sounds like, that's what I hope.
It's going to be very sad. All right, now what do we do? And the 45, yep. Okay, now what do we do? We check, but are we going to swap? No, we're done. All right, let's do it one more time. We're going to remove the 56. And we're going to replace it with the -17. All right, so it's still balanced and left justified. We've only done one swap, which is O of N. O of 1, sorry. Ooh, that was bad. O of 1. What do we do now? Yeah, swap with the 45 because the 45 is the largest of the three. Okay, now what do we do? With the 37, because it's the largest of the three. And then with the 10, yep. And then do we do anything else? Nope. All right, so. Again, I said I do things 3 times just to make sure it's clear. So just for clarity, we'll do it one more time. We're going to remove the 45. And we move, which number do we move up? -17, yep. All right. All right, what do we do next? Yep, with 37. All right, then what do we do? Yep, the 10. Then what do we do? Yep, swap over time with the 5, -5, sorry. I don't know why I just did that, but I sure did. Let's try that again. There we go. Okay. So, what is the big O of sifting down? Yeah, so it's also log of n. Because the removing is O of 1, and then how many times do you sift down? At most log of n, because it's balanced and left justified. So it's guaranteed log of n, actually. This is what's nice, is even worst case scenario, it's log of n. Okay. Anyone notice anything else?
The right side of our heap hasn't changed at all.
Yeah, that's because we haven't, well, if I were to, let's remove another one. That just happens to be the way the numbers were working. Let's put in a 37. And then negative 17 is going to go up there. Who do we swap with now?
17.
Now we swap with the 17 because 17 is bigger than everything over here, right? Yippee. All right. Perfect. Could just remove the negative sign, but whatever. Now what do we do? Yep, swap with the 10. Yep. Is it a heap? All right. So yeah, it just had, the data went that way that time. That's all.
I'm guessing there's going to be like an easier way to keep track of the leftmost child in the bottom row with the array.
Yeah, because it's the end of the array.
How would this remove work, seeing as both of them are 10, would you just choose the left? Or-
Yeah, you just use one.
Okay.
Sure, the left. It doesn't matter. Good question. All right, so sifting up, log of n, sifting down, log of n. Anyone else notice anything?
So it comes out in a sorted order.
It comes out in a sorted order. Ah.
Sorted.
So in order to create the heap, what's the big O of creating the heap? Every time you add, it's log of n. How many times do you add? N times. So it's n log n to create the heap. How much is it to sift down or to remove? N log n. N log n plus n log n is still, and yeah, it's just n log n. So that's heap sort. We're going to go through it though in the slides.
Sift up and sift down are in log in? You
What's that?
said sift up and sift down are in log in?
No, sift up and sift down are log n, but if you call them n times, then it's n log n. All right, so suppose we discard the root. We got to move the 11 up there so it stays balanced. Great, but now we have to sift down. So only the root lacks it, so we can sift up the root, which is really just sift down. So the 22 is larger, so it swap that. And then the 22 again is larger, so we swap that. And then again, the 21 is larger, so we swap that, and we're done. Okay, great. Notice that the largest or a largest is in the root. We can repeat this process until the tree becomes empty. This produces a sequence of values in order largest to smallest. Oh, that's nice. Sorting, so hopefully, because the binary tree is balanced and left justified, it can be represented as an array. Here is the whole point of why we're doing things this way. You can now represent this as an array. Our operation on binary trees can be represented as operations on an array, or on arrays. To sort, you heapify the array. While the array is empty, remove and replace the root, reheap the new node. Okay, mapping into an array. That's really the big trick. We'll talk, heap sort should make some sense once we do all this. Here we go. Here's the array representation. Wow, these numbers are slightly off. Notice the root is at 0. Root's at 0. The final node on the right at the bottom is 11. Notice that 25, its two children, 22 and 17, come right afterwards. But 22's children are the next two, and then 17's new children, the 14 and 25. So it's going like this, guys. In the array, you're storing it 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? All right. Does that make sense? Okay. The left child of index I is 2I plus 1. Let's do that for root. Let's see, I is 0, so 2 times I plus, well, that's 0 plus 1 is 1. Okay, great. Let's do that for, let's see, this 22 was at 4. So 2 times 4 is 8 plus 1 is 9, which is at 21 right there. This is slightly off, sorry guys. Well, it works there. So the right child is just 2 times I plus 2. That's how you can find all the children.
That's even easier than pointers.
Well, maybe easier than pointers. Depends. Some people get, when they try and write this out, they get tricked up. Don't know. Children of node 3, which is 19, is 18, yeah, 7 and 8. All right. because 3 times 2 is 6 plus 1 is 7, which is where the 18 was. And notice that the right one's just right after it. Okay, so removing and replacing the root. If root is the first element of the array, the rightmost node, okay. All right, let's, yeah, we'll keep going with the slides, and then we'll do some coding a little later. First is the root is the first, the rightmost node at the deepest level is the last element. So if you want to, oh yeah, here's the trick. If you're trying to sort the array, you just swap them. So, because now you know 25 is the largest, and you decrease the size of your heap. You pretend the last index is now 11. Of course, now you need to sift up. You got to reheap. And when they finished doing that, the 11 ended up right here. And then you do the operation again with the 22. The last is changed, so repeat until the last becomes first, and then it's sorted. Well, let me pause here because I went a little quick. Y'all see what it's doing here?
It seems not
Not quite. What's that?
So will you be doing this with pointers and or arrays?
I highly recommend you just use an array.
Okay.
Otherwise, you'll be sad. You'll be very, very sad.
But without a vector, it would be hard to like add and remove elements from it. So
Yeah. Usually when you use a heap, usually when heaps are used, you know the size, or you know what your buffer size is. Because you're either in a situation where you need to convert something to a heap real quick, do something with it, and then give it back, or you're in a situation where you know I have 4 kilobytes of memory. Let's pretend that whole thing is the entire heap. So that's usually it's one of those two situations. The heap, the thing about this data structure, it's one of these structures that people tend to forget, but ends up being incredibly useful for certain situations. So you probably won't be using this too often. I'll admit that, but when you need it, it shines very well. Because it's very good when you have limited memory, especially then. All right, so heapify the array. Heapifying the array, we add end nodes. Each node has to be sifted up, possibly as far as the root. Since binary tree is perfectly balanced, sifting up takes log of n time. Notice that is the big difference between the heap and the conventional binary search tree we've talked about so far. So the binary search tree could devalue into a linked list where everything goes along the left or goes along the right. That could happen. But in a heap, that cannot happen because of how we're doing sifting, or how we're creating it. So we're guaranteeing log of n time. Since, of course, we're doing this n times, 1 for each element, and there's n elements, heapifying takes n log n. The rest of the algorithms, why it isn't empty, remove and replace the root and reheap the array. We do the loop n times, actually n minus 1, but that's okay. We have to remove one of the n nodes each time in the while loop, and removing and replacing takes O of 1, but the reheap method takes log n. There we go. Where are you? Yeah. Oh, since the binary tree is perfectly balanced, it takes log of n time for each reheapify. Okay. Therefore, reheaping takes log n, and the whole while loop takes n log n. Heapify. Here's the whole thing. Heapifying takes n log n. While loop takes n log n. The total time, of course, then is n log n plus n log n. And it's the same, of course, as O of log of n time, because we're only caring about the bounding. Just because you have a constant in front of it is not important for big O notation, at least not yet. Any questions on this analysis? Because this is the final sorting algorithm of the class. Hopefully. Yeah. I don't have any reason to go into other sorting algorithms. This is usually the last one I teach.
bubble sort.
I did bubble sort. I did bubble sort, selection sort, insertion sort, quick sort, merge sort, and
There's
here's
so much more to it.
I think we haven't done enough justice to bubble sort.
Yeah, okay.
There's bad.
You're feeling bad for bubble sort, is that what it is?
Give it a bad rep.
Give it a bad rep. It's the easiest to code, right?
So what if it's the slowest?
So it'd be the
I mean,
best,
the
right?
speed really isn't something to care about. Do we always need to be in the fast lane back class?
Oh yeah. Do I need to play Linus for this role? If you're, it depends on your application, actually. Right? There you go. Isn't that what I said the whole time? It depends. It's not even a data structure. It's an algorithm.
So does that mean we didn't get points when we put that down?
I went ahead and took that. Oh, good. The end. All right. All right. We should go code this, right?